Okay, let's start by trying to solve the puzzle that Gauss did when he was a kid. So remember that the puzzle asked to take a sum of the first 100 numbers. So 1 plus 2 plus 3 plus 4 all the way up to 100. So how would you do it without spending all this time calculating the sum? So here was Gauss' idea. Let's write down numbers 1 to 100 and then write down, well, probably wouldn't want to write all of them down, but if you did, numbers from 100 down to 1, you would notice that every pair, 1 and 100, 2, 99, and so on and so forth, sums up to exactly the same number, to number 101. And how many of those do you have? Well, you have 100 of those. So if you sum up 1 plus 2 plus all the way to 100 plus 199 so on to 1, but sum it up as 1 plus 100, 2 plus 99, and so on and so forth, you'll end up with a sum of 100 copies of 101. Since we know that we wrote the numbers down twice, our final answer is 100 times 101 divided by 2. So the sum of numbers from 1 to 100 is just 100 times 101 divided by 2, which is 5050. If you do it this way, it doesn't take you that long to calculate the answer. So Gauss' teacher had to find something else to keep him from being bored in his math class. So here's one question. What if I give you a different list of numbers? Not 1 to 100, but 1 to 50, 1 to 1000. How would you generalize Gauss' trick in order to compute the sum? So here is the formula that you can come up with if you stare at this example. So what you do is you write the numbers down from the smallest to largest. Underneath you write them down from largest to smallest. So every number is repeated twice. And the sum of every number with a 1 above it will be n plus 1 if you have n numbers, right? So in your very first column, it will be 1 plus n, like it was 1 plus 100. Then it will be 2 plus n minus 1, and so on and so forth. And there will be n of those columns. So the total sum is n times n plus 1 divided by 2. Well, this is our guessed list. Let's try to prove it. And let's use the well-ordering principle in order to do this. So just how the well-ordering principle works. Let's start by contradiction that it doesn't work for all the possible numbers. And let's take the list of all numbers for which this formula doesn't work. Then, by well-ordering principle, if this set is not empty, then there is a least number k in this set, and we will show that this k cannot exist and conclude that there is nothing in the set S, so the formula works for every n. So the bulk of the work is to show that such k cannot exist, and we'll do it by proof by cases. We will first look at k equals 0, and then we will see what happens when k is greater than 0. So let's start with k equals 0. For k equals 0, we just plug it in. What is the sum of numbers from 0 to 0? Well, it's 0. And what does the formula give us? It's 0 times 0 plus 1 divided by 2. Well, I could have stopped at 0 times whatever, because 0 times anything that's finite is a 0. Good. So that smallest number k in the set S cannot be 0. If it's not 0, it should be greater than 0. Let's see what happens in this case. So first we start by writing out the sum by expanding out the very last element. So remember that the sum is 0 plus 1 plus 2 plus 3 all the way up to k. You could also write it as a sum of numbers from 0 to k minus 1 and then add k to it. This is by definition of the sum. So since k was the smallest number for which the formula didn't work, for k minus 1 it should work. And remember, since k is greater than 0, there is a k minus 1 which is greater than or equal to 0. So we could write the sum from 0 to k minus 1 to be k minus 1 times k over 2. Because k was the smallest number, that's where the well ordering comes into play. So it works for k minus 1. Now it's just a calculation. So what would be k minus 1 times k divided by 2 plus k? If you multiply things out and plug in the numbers, compute things, you'll end up with k times k plus 1 over 2. But wait a moment, that's exactly that formula. So it does work for k when k is greater than 0. So it works when k is greater than 0. It works when k is equal to 0. It works for every possible k. So that means that there is nothing in the set S, which means that there are no bad numbers for which the formula doesn't work. So the formula works for every number. So now you probably already seen what structure those proofs by well ordering principle have. So we start by wanting to prove some kind of claim of the form for every x, some kind of p of x holds, where p is some predicate, some formula. Equality, inequality, something more complicated, just something that's either true or false. And then the proof goes like this. Suppose that p of x doesn't hold for every possible x. Let's collect all those bad x's for which p of x is false into a set S. By well ordering principle, there is a smallest element in S. And then we just need to prove that such k cannot exist, for which we will use the fact that it's smallest. And often we will need cases k equals 0 or k greater than 0.